Speagle for our seminar today. Josh wears many hats, but just to give a brief chronology, Josh did his PhD at Harvard working with Dan Eisenstein, Doug Finkbeiner, and Charlie Conroy. His thesis was on mapping the Milky Way in the age of Gaia. Since then, he became a Banting Fellow and a Dunlap Fellow at UToronto, and shortly after was promoted to assistant professor. And now co-leads an Astrostatistics research team with Gwendolyn Eady. I guess a lot of his work involves wide field imaging and spectroscopic data. And, I really look up to Josh as a sort of practitioner of these methods, but also Josh has done a lot of more deep thought in terms of these methods and, in general is interested in statistical learning and AI, interpretability, inference and computation, and data-driven discovery. And I think he's a real champion of open science and reproducibility for these types of things. And, when I first met Josh, I guess he was a young grad student working on this nested sampler called Dynasty. And since then, it's been a very exciting career for him. So I'm really happy to have him today. And let's please thank him.
That's a great introduction. Yeah, it's my first time visiting Berkeley. It's lovely to be here. I was so excited when Richard, asked me to come, and I thought that rather than talk about anything like specifically related to astrophysics, it would be a much better use of my time to just rant about a bunch of stuff related to machine learning and AI, especially in the Bay Area. So of course, there could be. You guys have never heard anything like this before. This talk is going to kind of like go all over the place. So if anything is unclear, just let me know. I'm happy to answer questions during if you have anything that pops up. Before I jump into it, I just want to say, as Richard said, we're a new group at University of Toronto. We're really lucky to have two jointly appointed professors between statistics and astronomy. We have a pretty large growing group. We have 7 postdocs, 6 PhDs, a lot of undergrads, and this very, very lovely logo designed by a previous postdoc, which I love. It's actually based on the original Hubble diagram. So that's the stars are actually aligned with the Cepheids, which is very fun. So anyway, you can do a superposition and see where we've had to slightly adjust to get the letters to come in. But yeah, if you have questions, we're always super excited to talk, and we think this is a very exciting field, and hopefully, something where it will continue to grow. The quick warning is you might say this isn't an astronomy talk, which means I'm going to talk a little bit about some of this data, but I'm going to talk more broadly, especially for this audience, about a wide variety of things and where sort of these methods come in and how they can use to do science. If you're interested in all this other stuff that I do, just go check out my website or ask me questions. I'm super happy to talk about it, and you'll see a small sampling of things, pun intended, as part of this. So, question, right? Why is AI and machine learning everywhere? In some sense, it's yes, we must usher in the machine gods quickly. But, before that, right, at least in astronomy, a lot of I think in lots of other sciences, one of the big motivations is data volume. So, we're collecting more and more data, and we sort of say, we need to turn to something to process this quickly. And these methods, they're really, really quick, or at least in theory. And also, in some sense, it's accurate. The amount of times I read a paper that says we used to use method X, and then we used this machine learning method Y, and it was better. And then it just kind of ends. That's sort of a generic thing. And it's kind of incredible that you can take the same method, right? You use a random forest, you use just, neural networks, and just apply it to any problem, and it just beats whatever was in that field. I'll get back to this later. I mean, that is something that makes it very appealing. It's also very flexible for this exact reason, right? You could take something off the shelf, you can run the same 3 lines of scikit-learn, you can get amazing results in most cases. This isn't enough, right? If we're talking about science, and of course, whenever you ask a question, I think there was a study saying that 90% of the time the answer is no. Those are also the best papers where the entire abstract is no. They exist. There's a handful of them. We have to think really carefully, what is it that we care about when we're doing science here? Are we just trying to predict a function? Are there particular astrophysical constraints or other constraints that you care about? Either hard constraints, soft constraints? Do we need to understand why it works? If there's some control system or thing that you need to optimize, maybe not, you just want it to be pretty effective, but maybe you want to use it to get some insight into a particular source. You want to understand weather phenomena, you want to understand particular predictions, supernova, the universe, all that great stuff. Errors, big one. What happens if things go wrong? How do you know about the data? You have some system for monitoring sort of data drift, data evolution. Right, and of course, in astronomy, this is not usually so bad, but if you're in any other domain, think medicine, right? Think climate forecasting, this is a big deal. What happens if things goes wrong, right? As soon as lawyers get involved, you know it's going to be expensive. And the way I like to think about this is I've had this like, I think that this like sort of GIF compilation is funny because it's very dated now. Both like GIFs in general, because no young people use GIFs anymore. And now I can refer to young people as a separate class because I've moved out of the census age range, smallest one. You know, like this is back when the Avengers was there, but it's also very real in the sense that I think this is exactly what happened to Marvel. You know, so I think it serves double duty here, right? The bigger question is, why do you use AI? It's shiny, right? Rich Sutton has this great short essay that is everywhere, but also that you can see everything in, you know, about the bitter lesson. The thing I want to highlight though is this particular one, right? The biggest lesson that can be read from 70 years of AI research is that general methods that leverage computation are ultimately the most effective and by a large margin. What does this mean, right? What are the two takeaways that I think you can draw from this essay? One is that these models will eventually win. Like if you give it enough resources being compute, data scaling, whatever, they're going to do better. So it's not surprising that they do better. And maybe it's surprising how quickly they do better, but it's not surprising that they do better as like a rule. The thing that matters, right? So it's not if, it's how. The how matters a lot. That's where all of the learning happens, right? How exactly is it out competing some existing method? It must be using the data that's there more efficiently. It must be learning things about that data. What is it learning? If you don't ask that question, you learn nothing. Other than that, you burned a lot of CPU hours and maybe heated the atmosphere just a tiny bit more than it would have been otherwise. You know, and one big thing, right, in terms of adoption in science is trust. If people give you a method, right, why is it that it's not being used? In astronomy and lots of other places, there are a lot of papers that use AI and machine learning. And I'll show some stats on this in a second. But there's actually very little uptake in big flagship scientific analyses. You look at giant collaborations and ask, where exactly are these methods being used? Often they are in specific locations as part of a much broader pipeline, but it's definitely not to do the flagship analysis. That science analysis, that's very old school. Nobody touches that with like some AI model, at least in astronomy. There's this wonderful paper by this group of researchers, I think at Harvard and Chicago, that tried to look into this. This is up to 2022. So who knows, maybe this has changed a lot because the agents are writing all the papers now. The main thing I want to highlight is down here on the bottom. So the thing here is that AI engaged work is spreading out over fields, but not mixing well with non-AI engaged work. Even though they find that the use of these methods and the citations have increased by about 13 times, right? Factor of 13. What's happened is that it's created its own sort of sub-communities. It's not actually merged or integrated with existing work. So there's whole new realms of science that have opened up, but traditional approaches have not incorporated them. Why? Right? I think this is one reason. You can also think about this way, right? If you're talking to a chatbot, let's just say this is ChatGPT, and it says, yeah, you have some conversation, that's dark energy, and you ask, why should we believe you? And it says, oh, because I'm an AI agent, right? I know what I'm talking about. Now we'd be like, I don't know, but maybe this is changing quickly. I got a submission yesterday from a student. When they had to acknowledge what AI they used, they said that they fact-checked their submission with ChatGPT. And between like you having to fact-check ChatGPT and ChatGPT doing the fact-checking has been less than 2 years, right? This is a real quote from a real person, right? And I'm not trying to single them out, but saying this is how quickly trust is changing, right? When we try and talk about results of other people in a paper, we are leveraging a lot of our own expertise. We look at someone, we say, what institution who have they worked with, where are they from? They did a PhD. We know that that gives them some amount of trust. We think that that training means that their results are reliable. The public doesn't know that, right? We don't know that with AI either. What ingredients does it take to trust these types of models? And how does it matter? In astronomy, this is huge. So this is a plot I pulled from the Astrophysics data system and then analyzed it with Claude Opus. So here's a bunch of results showing different citation rates. The key thing here, red line is deep learning, purple is Bayesian, blue is MCMC, green is method sampling, orange is simulation-based inference or likelihood-free inference. And like, this is in, by the way, square root. So look at that, right? now in astronomy, you are almost as likely, if not more likely, to see machine learning used instead of the word Bayesian. That's crazy. And you ask why. And scikit-learn was published right around 2012. And look at this, right? And TensorFlow, PyTorch come out right around 2015. JAX starts coming out around 2020. The curve is clear. It's software. People are using these methods because they become easy, because they become accessible. This is also true for things like traditional methods like MCMC. So if we zoom in, for example, this is also true for SPI. So in astronomy in particular, if we look at, for example, a search. So this is one, we go up top, you can zoom in. It says, okay, I just look for any paper that mentioned MCMC that was published between the year 2000 and 2026. Sorted them by citation. What do we see in this list? Okay, we have a couple big flagship cosmology analyses. Here's Planck, here's WMAP, here's Planck, and here's WMAP. Great. 5 humongous papers in astronomy that just happen to use this method. Second one is SciPy. Okay, makes sense. I think a lot of people use code. The fourth most common is a single software package that everyone in the field uses. And I can confirm that everyone in the field uses because I checked for the top 100 and there's no other papers that are this high. If you look at the number of papers that use MCMC and the ones that cite this particular case, this is now showing a plot. The number of papers on this one is the bars. The fraction is on the other side. That is the line. So it's asymptoted where about 45% of all papers that use markup chain Monte Carlo cite this particular package. So that has driven a lot of adoption and has been hand in hand with the increase in Bayesian inference. And for good reason, I think this probably is that almost every analysis that uses markup chain Monte Carlo uses this code. Now, you might say, okay, so people are using these methods a lot more. Do they know how they work? So, okay, my claim is that most astronomers don't. And that's because if you do a plot like this, which is here's the fraction of papers that cite anything about MCMC. So anything that mentions burn-in or related things, so warm up, tuning, whatever, anything that mentions any proper diagnostics at all, effective sample size or whatever, there is no change. See, look at this. You have a humongous increase in people using it. This line doesn't budge. It's still about 5%. This is saying people are comfortable using these methods. They trust them, but they don't know how they work in a clear amount of detail. There's something else happening here. This is true for deep learning too, right? So that's the motivating question, right? We always ask about what these things can teach us about. I'm not going to talk about that. I want to ask how, right? How is it that we can generate trust in these models? How are people going to use them? Can we come up with good practices? And I want to sort of start that conversation here. Very big picture. So I'm trying to connect it to a lot of different areas so that when you sort of think about using these approaches, you feel that they're a natural tool that you can use. You can try and figure out the right questions to ask when you see them in other papers. So that's my sociology rant. Now let's talk about like non-sociology stuff. So this talk is going to have 5 parts. One's going to be talking about how we build trust with regular models. Why do people like things like linear regression? What about deep learning? How do we leverage what we do here? How do we get this into uncertainties? Scaling, of course, big here. And then obviously, how do we learn? I'm not going to have defined answers for all these things. I just want to really start the conversation about thinking about them in a very big picture sense. This is very much inspired by papers like Michael Betancourt's A Conceptual Introduction to Hamiltonian Monte Carlo, which I just loved. It really kicked off my view that this is a good way to approach a topic. I was inspired enough, I wrote a second one in grad school. My supervisor was a little worried. And then now hopefully this will turn into like a third iteration of this related to deep learning. Okay, so let's back up. I'm a stats guy, which means we're going to do linear regression. Woo! Right? All right, linear regression. Why do people like linear regression? It's easily interpretable. I look at this equation, I can say, great, I have some coefficients. These are associated with particular variables. I know what they mean. They have a very particular impact. Fine, right? Linear regression is great this way. One way to think about it is if I change my output with respect to some variable, this describes exactly how that change is modulated. Okay, fine. What if I change this a little bit? I can transform my data. Often in astronomy, we do everything in log space because then linear regressions look better. But in lots of other things, you might think about phases, cosine of something. You might think about other transformations, polynomial fitting, curves. There are many possible ways to transform and think about your data. So, okay, like does this still hold? Kinda. Now your coefficients are with respect to these transformed parameters. Or you can think about them as, so you can sort of say, okay, this is with respect to these transformations, or I have to take some other sort of like term into account to do this. It's still somewhat understandable. You can start adding interaction terms, saying like, what if I have two things here? You can kind of think, well, what if I hold one of these constant? And so you have a line that sort of has a slope that changes if you change one parameter, for example. So as a function of x2, it sort of like shifts around, the plane moves a bit. It, interpretability starts to get a little bit more difficult, but we're still there. So I put quotes around it now. There's like some extra terms that come in, but we still kind of can reason what exactly this model is doing. We can get some insight into this. Uncertainties, linear regression is also great. We put on some uncertainties. I'll call the noisy data here, generally tilde, as the notation I'll use in this talk. We can say, oh, this is from some normal distribution with some unknown mean, and maybe my measurements of uncertainties. I can sort of model statistically, everything goes through. We're really happy, right? The input and output uncertainties you get are explicitly connected. You know exactly how one is going to translate into the other. So that's nice. Now, what's another way to think about this? That's the model side. What about the data side? Linear models are also great because they feel super intuitive on the data. You make a plot like this, and you say, okay, well, there's some risk that I've gotten the wrong relationship. I think that the universe or this model is simple. I have some very complicated data, but there's some simple underlying principles. So as I make my model more complicated, it's going to do better and better. But I make it too complicated because like the world is not that complicated. I'm going to start fitting some noise. And then it's going to get worse. So my training performance will get better and better, but my testing will go up. This super intuitive, right? There's a sweet spot, and that sweet spot means that meaningful explanations of data should simplify things. They should be insightful. This is Occam's razor. Now, there's another way to think about this, right? Overfitting is that when you have too many, you often memorize the data. People talk about degrees of freedom. People think about non-generalizability. There are lots of ways to think about what happens here. But in sort of standard case, you could imagine you're interpolating between some data, and you end up with a lot of very high variance as your points overshoot a lot of the data as you're doing this interpolation. And so you can memorize a lot of things. Your function gets very complicated. You have a lot of high frequency structure. Either way, that makes a lot of sense, right? Underfitting makes sense. Overfitting makes sense. That sweet spot, it makes sense. So let's use that as a scorecard and say, what does this look like for linear regression on the left? And then what about for deep learning on the right? Do we have something that's interpretable? Yes, of course, linear regression is interpretable. It has these built-in uncertainties. It also lets us do model selection in this way, right? There's sort of a sweet spot, and it gives us insight. The coefficients mean something. So amazing. My claim is that we need to have clear answers to all the ones on the right before people use these methods. They don't need to understand how they work. They just need to know that you can actually extract these types of things from them. That's the important takeaway here. So I've been trying to work on this a bit, a lot with a postdoc, Pete Prateep Day, who's a Schmidt Sita Dunlap fellow at Toronto. So if you have questions or feedback on the material, either some details or sort of presentation, definitely contact us and we will try and incorporate this into some draft that we're writing up. All right. So that's linear regression. And we can all sort of like breathe out and say, great, we're out of that one. I don't want to see that again. I've seen enough of fitting a line, you think. All right. So how can we trust modern models, right? Let's just start here. So we say, okay, well, what is the difference between a simple model and a modern model? Just the number of parameters. So what happens if you add more parameters? Surprise, it does better. So as you increase the number of parameters, you get this famous double descent phenomenon where you have this classical regime. You end up with this point where it's sort of interpolating the data. And then as you add more parameters than data points, you actually do better. And you end up with the second minima. And that one actually does better than the original. So your model actually improves. I always like to think of this as like the Palpatine moment, in like the old Star Wars movie. I think they did a re-release of this recently too, where, he's like, I'm so weak, die. And then, and then Anakin, of course, comes in and like makes sure Mace Windu loses. But yeah, it's a fun moment where it seems surprising at first glance, right? So I'm going to make some shortcuts, but conceptually, I want to argue why this happens, how to think about it. and how you can leverage this essentially to get lots of insights about how your models and your data are behaving. So the first thing I want to say is that deep learning is extremely mysterious. Otherwise, these companies would not have $500 billion. But at least to some extent, if you wanted to try and make an argument, I would say here's a very complicated model, and I can divide this model into two parts. Part one is all of that stuff that does crazy things, and part two is the end. And the end part is actually pretty easy because it's just linear regression. Every model at the end is doing linear regression or linear regression and softmax. It's just usually it's linear regression or some generalized linear model. So there's a linear layer at the end of everything. So you can think of it as saying there is some feature transform. This is learning some feature. This whole giant thing is learning how to take my data, transform it into some feature, learn this function, which I'm going to call phi, of my input data x, and then it just learns a bunch of coefficients to do linear regression. So it's linear regression with the bunch, and of course the magic happens in the extra stuff, right? That's where all of the stuff happens. But it's good to think that what it is doing in some ways is linear regressionizing your problem. It's what are all the ways in which I can make everything fit onto a hyperplane as much as possible. And hyperplanes are great because you can move around on them in all these different directions, they decompose, and my predictions look beautiful. A digression, of course. I'm going to bypass exactly how this happens, but a lot of this is intimately tied to optimizing gradient descent. I just want to comment that it does not rely on any stochasticity for batching. It doesn't rely on fancy learning or optimization algorithms. You can get this with normal gradient descent. It also does not even rely on nonlinear models. You can show this happens with linear models. But all of these things help, and they're all very important for real things. I'm not going to talk about reinforcement learning. We're just going to pretend they don't exist. I'm going to show you that limit should exist, that it will do better in infinity. I'm not going to cover anything in between. So I just want to make that super clear, but I'm happy to talk about lots of dynamics here because it's very rich. And also, this is probably why Adam has 200,000 citations or something. It's turns out optimization is super cool. So what does this mean? One way I like to think about this is that it gives us a dual representation. So you can think about when you're fitting some function, either you're fitting this curve, right? The super complicated curve to accomplish some task, in this case, classification, or you could think of it that you're learning some transformation that makes it so you can fit a plane. Those are the same. They are the same thing. One can always be phrased in terms of the other most of the time. So you might say, okay, this is great, but why do we need so many dimensions, right? Why does models need to be so big? What's going on here? And for this, I'll give some examples how augmenting your space, going from 1D to more than 1D, helps you. Some of these you might be super familiar with, but hopefully this is a good review. So on the left, you might want to do classification between the blue squares and the yellow circles. And this is really hard to do if you only have one dimension. So what you do is you instead add a second dimension, which is squared, and then you draw a line on the second dimension and boom, perfectly separates. You can do this with things like this if you use a modulus operation, for example. So again, different transform, but still gives you the exact same thing. It's a feature that you learn. Here's one in 2D. You learn some sort of radial thing. It separates out, so you can draw a hyperplane through this direction. In all cases, the idea is that when you lift your data up to a higher dimension, you augment the data, it allows you to have this linear representation that is more generalizable. So you can think of it as fitting some curve that corresponds to some ring, but it also can definitely be thought of as a hyperplane. This is a huge deal. It really helps you understand a lot of things about how these models work and also the types of features they want to learn, because they want features that decompose this way, often because they make the model more robust. One other way to think about this is, at least in lots of ML, is called the kernel trick. This is pretty classic. So we've actually seen this idea. So we do something like this before. We transform our data. We started with x, and then we made e of x, and we made cosine of x. And that's going to give us some transformation with some coefficients of the data. So our phi here is going to be essentially e, e of this, and then cosine of this, and that's going to be like our 2D transformation, for example. When you solve for A, you actually get this pretty cool result where you actually never care about phi. You only care about the inner product of phi with itself over all of the data. So you never actually need to explicitly compute these transformations. That's what's often called the kernel. This is really good computationally, but what it also means is you can do some crazy stuff. because one is you can rephrase all of the thing I just mentioned in terms of kernel regression, which means you just apply these kernel operations and then everything looks like a normal linear regression. But the second is that this means that you can actually implement features that you either don't know or that are infinite dimensional, or that you want to apply transformations to things that are very easy in kernel space, but very hard to do in feature space. So implications for this is that you can think of feature transformation and feature learning as actually correlation learning. It's structure learning. What matters is not the transformation. What matters is the correlation structure across your data induced by the transformation. It's how it changes the distances and the relations between points. The transformation can be infinite dimensional as long as the product's defined. And so this gives us our dual representation where both of these things are equivalent to having some kernel. Here are some examples of what those look like. These are some common ones used for Gaussian processes, this radial basis function, here's periodic, and here's linear. These can be kind of weird because this is sort of saying like for two data points at some distances, how are they related to each other? So I actually like this other view, which I'll show you now, which is actually drawing like functions from this kernel. So here's an example of like what a squared exponential looks like. Here's the type of things you give with periodic functions with linear kernels, which give you lines, rational quadratic, which are infinite mixtures of these things, locally periodic things, and you could do more complicated stuff too. The idea is that you can, all of these things, features, kernels, curves, they're the same. And so these three perspectives, right, you can go from one to the other, essentially in these three views, right, as either 1, 2, or 3. That's kind of the big takeaway. Now, why am I spending all this time doing this and not talking about neural networks? The answer, of course, is that this is a neural network in some respect. There's some really amazing results where you can show that in the infinitely wide limit, neural networks actually do have a kernel, both initialization, the neural network Gaussian process, and of course, during training, the neural tangent kernel. And what this tells you is that the choice of architecture in your model directly tells you a prior or belief about how that correlation structure exists in your data. So when you create a model, you are in fact telling the model something about how you think the data are behaving. You're making choices before you even fit anything, like priors. These are examples from the paper on neural network Gaussian processes where they show sort of what these things look like. The top shows samples, sample function draws. The bottom shows the behavior with depth. So as the model gets deeper. The shallowest one is over here, which has this very strong dependence on angle. And then as you get deeper, they become flatter, which means they can model more and more complicated things that are less correlated to each other. And so there you go, deep learning, right? That's one reason why things matter.
Wait, so I don't understand what that has to do with deep, because the kernel is actually infinitely wide.
Yes, but you can have infinitely wide layers that stack on top of each other. Yeah, so it's finite depth, but infinite width. Yeah, so this is also connected to things like deep Gaussian processes, where you sort of have nested Gaussian processes with each other as well. But the idea is that the effective kernel from many sets of infinitely wide layers will actually change between the input and the output. Hopefully that makes sense? Ish? I'm happy to talk about it later as well. One of the big takeaways from this, though, is that this shows that architecture matters. It's like a choice you're saying about how you think the data behave, but also that it kind of becomes not so useful to think about like individual neurons or one parameter. Like what matters a lot in kernels is not one parameter, it's the structure that's induced by many parameters. You know, a feature transformation is made of many parts. People often call them circuits, or you can think of particular components of a model. So it's less useful to think about, oh, this one neuron or this one thing. You want to discover what is that group? What sort of feature does that learn? What type of structure does this correspond to? And of course, with real models, which do engage in feature learning, some of this principle applies, but it becomes a little bit more complicated in practice. But if there's anything you take away from it, it's that there is a connection, right? There's some connection between structure, the model you pick. So deep learning is effective because it turns out that when you have a really deep model with some of the assumptions, the correlation structure it ends up generating is actually pretty universal across lots of data. So on this card, you might say, is it interpretable? Kind of yes, at least in terms of groups, right? So in theory, it's not an individual parameter anymore that matters. It's groups of parameters, and it's the structure across the parameters that matter. And we can understand some of that structure or at least we are developing tools to understand some of that structure. But at least that shows us why we have a foothold into this. Okay, so what about uncertainties? Now, uncertainties are difficult, right? We have lots of different measurement errors and processes all across astrophysics and across all the sciences. You have uncertainties in your inputs, you have uncertainties in your outputs. You also might imagine model uncertainties. These are often the difference between aleatoric or sort of statistical, like epistemic or systematic uncertainties, between what you think you know about the model versus the data. So you could have things about your model, your neural network that has a bunch of things there. So these all can get kind of batched together. You can often propagate some versions of these through things like chain rule, but it's very difficult to understand the impact that one set of things have on another. I'm not actually going to talk about most of these things because that's a whole separate talk. What I will just try and mention is that there are principled ways to think about and try and account for all of these different sources of uncertainty when you go and attack these problems. And particularly during training in astronomy, this is important. So I originally had in the first version like some proof showing how this actually works, but it turns out it's way too long. So I will just leave this as an exercise, or say you can go read some papers. But all I just want to say, the real thing is that if you think you know something about your data and the measurement errors in your data, so if you know the measurement process that uniquely specifies a particular loss function or negative log probability, given your noise model and what you think your data is doing. So in this case, your noisy data, again with tildes, will depend on something related to what you think your measurement errors are on your inputs and your outputs. And so what this means is that the data properties should drive both the loss that you choose when you're training your model and the architecture that you're using. And they should be connected when you're designing a model and when you're fitting it. And you can understand this from sort of these type of conceptual arguments. Inference will require marginalizing over some of these things. And this can be a little bit of a pain, but you can definitely figure out how to do this using lots of log sum x operations. You can augment your training data, which can be a workaround. But I want to say that if you just naively like Monte Carlo uncertainties and don't think about it, you can actually double count your uncertainties. And so you do worse than if you just pretend they don't exist. So if there's any takeaway from this, is that if you have uncertainties, you're not sure what to do, don't do anything. That's in fact better. Let the model try and marginalize over it. If you try and do something naive, you actually could do worse. There's some really nice counterexamples I can give, but if people are curious. Just to show that this actually totally works. So this was work led by Zichan Sung, who's at Tsinghua in Beijing. We've also done some work with Bingxie Wang, who's at Princeton now. We call the code SBI++. But more or less, like you write down these functions and you say, I have some very noisy data, but I think I know what the error bars are. I want to infer the true noiseless estimates of the population. Totally works. So here's an example where these are the marginals at the top, but the main thing is that observations are in gray, intrinsic is in blue, and then reconstructs in red, and you can see the results, right? So we recover that donut from the cloud of points on both sides. We're not perfect on the double moons. We kind of like merge them a bit at the center. But in any case, like the fact that we can recover some general density from these very, very noisy estimates is exactly the point. Turns out that hierarchical inference and population inference, like a very old statistical method, translates very well into ML. You just have to write down the correct loss and the correct way of doing the marginalization. So this is just saying that like you definitely can incorporate these things into models. And at least what I've found is it goes a long way to getting people to trust your results. If you can show, look, if you give me different noise properties, different data, different types of selection, my model knows what those things are and knows how to account for them, I can still perform well, rather than just being always out of distribution if my measurements change like a tiny amount. This, of course, also begs the question, why can't you also just do this in the predictions too? Your neural network model doesn't have to predict a number. You can also predict a probability. So this is very similar to quantile regression, where the idea is that rather than predicting a mean, like in linear regression, you can predict different quantiles of the data. And if you predict, all different quantiles, that's sort of equivalent to predicting a probability. And so it's not such a big stretch to think that you can also predict the distribution too. This, of course, is now very, very popular. So people talk about diffusion models and normalizing flows and flow matching and generative mass things. And there are tons of different ways to do this. But the main thing is that you can definitely either sample from this method from like distributions without knowing them. You can predict the distributions themselves. You can predict moments of those distributions. There are tons and tons of ways to do this. They all work. And they all can be adapted in various ways to make this type of thing possible. And this is important because it means that when an observer or a practitioner gets your function and makes a prediction, you give it, it predicts uncertainties, and the practitioner who then knows sort of what types of uncertainties to expect will kind of look at it and go, yeah, these look about right. You know, in practice, I think a lot of people are more comfortable with vibe errors than they think. And as long as you can show them that your model gives you the right vibes, then they will be much more likely to use it. And hopefully you can also show quantitatively that your error bars are very robust and well calibrated. Just as a great example of this, so this is like one of the little Astro projects we've done. So one of the things that I was really interested in since I was an undergrad was actually getting ages for stars, because we take pictures of the night sky and then stars don't tell you how old they are. They just look like they have different colors, and then you don't really know what they're doing. One of the ones that I think is really cool is this idea called gyrochronology, which is that stars rotate. And so the rotation rate depends on magnetic braking. So over time, stars will slow down. This does depend on stellar mass. So it depends on like the mass of the star and the age of the star. And although stars start with a large dispersion, they actually kind of converge to a couple common sequences over time. And now we can measure rotation rates essentially by looking at things like sunspots or stellar activity. But if we see variability in other stars and we can measure how quickly they're rotating, in theory, we should get an age. So that's the idea. The problem is that reality is really messy. All of our models to predict this were terrible, off by like 2 orders of magnitude. And we only have one data point where we really know all the answers, which is the sun. And so a sample size of 1 doesn't really help you. And so with the grad student at Toronto, Phil, he managed to very painstakingly assemble about 7,000 stars across 30 clusters where we can get ages from other methods. And that's what we get here. This is a plot showing the rotation period on the y-axis, the color of the star on the x-axis, and the color of the points is the age. And you can see there is a gradient, but it is pretty messy. So what we tried to do is every single one of these points has an error bar associated with it. There's also errors about whether we've associated a star with the right cluster. So we have some concatenation concerns. There might be outliers, even if we do all of this properly. So we had to write down some very complicated function to do this. But if you do that, we then train this conditional normalizing flow to predict the distribution of rotation periods conditioned on a couple of different things, including measurement uncertainties. And this is the result. So I just want to show you this wonderful animation. So this is showing the density as a function of time from the data that you just saw. And you can see as it grows, you can see the sequence converge. You get this nice kink. It evolves over time. And look at that. It's beautiful. It turns out that stars really are extremely well behaved, especially sort of in this upper region here. And you can see again, upper means it's slower, that stars sort of spin down over time and in a way that depends on this color, which we often use as a proxy for mass. And this is great because we didn't have any theoretical models that could predict something that's this complicated. And again, as a reminder, the smoothness across this is actually a consequence of like the architecture that we picked and some experimentation. There's also some work using Gaussian processes that have done this too. But this is really cool. And we showed this works. If we essentially leave training data out and we try and predict it using various versions of the model, we actually get pretty good age estimates. We get about 20% or 0.08 dex. In astronomy, that's pretty good. So we were very happy with this result, saying that the model is actually quite robust to all these different sources. And of course, it takes into account all of these things like uncertainty and messy data and contamination and other stuff. So again, it's not saying that you have to reproduce everything, but it's showing that like you can take these concerns and build robust, trustworthy models that give you, in our case, we just wanted to see what this relationship looked like so we can study it more. So we didn't have good models of it in the first place. So yes, we could definitely use, these methods to deal with built-in uncertainties. And I'm just going to completely bypass what an uncertainty means. But if you want to talk about uncertainty calibration and lots of other things, I'm happy to do that as well. Okay, so this is now about scaling. Right now we're talking about model selection. How do we know the right model to pick? And this is a little bit of a different question when it comes to a lot of machine learning. because there are a couple of things missing from this picture and from our understanding. In the classical regime, it's nice and easy. The best model is kind of this one, right? But in machine learning, it's like, well, why isn't the best model like infinitely many parameters, which seems to be what people have converged on? And in some sense, that's true. The bigger your model gets, the better it's going to be. Even if it saturates, it's sort of more of a trade-off, like a sort of cost-benefit trade-off about how long it takes versus how good it is. But there are some things missing from this plot. One is that this thing says like capacity, but this kind of is conditioned on the model architecture. If you choose different assumptions, you get different correlations and different efficiencies for how well that model can associate with the data. I like to think of this as sort of alignment between the correlation structure that the model assumes, the eigenspectra of the model, and the associated underlying eigenspectrum of the data. The closer those things align, the more efficient the model is going to train, and you don't know ahead of time what that is. The second is data, right? This sort of is this interpolation limit, but it seems overly simple. If you added more data, doesn't this kind of like move to the right? And so your model kind of has to catch up by getting even bigger. What happens if you have infinite data? Like at some point, it kind of has to just stabilize, right? Like you have a mean. At some point, you're like, I've learned the mean, it's okay. I don't need any more. And this sort of like interpolation limit can't quite track with data one-to-one. In language models, we could talk about chinchilla scaling and things like this, but at least naively, there is some data access here that we're ignoring. Third, of course, is compute. This is like the result of after we've trained our model to convergence. But if we stop early, when our model begins, it's somewhere up here, right? And then over time, there's some like slow movement down to get to a particular point. If we stop early, what does that look like? So I like to think that this isn't like just a curve, it's sort of like a whole waterfall or landscape of possible solutions, and we have these knobs to tune in all these cases. And this is sort of what a lot of Silicon Valley is really obsessed with, is trying to figure out, how to optimally tune these things, both for forecasting, like running experiments with small models that you can then immediately scale up to big models, but also just trying to figure out like how long it's going to take, what should I expect, what are the performances I'll get by doing something like this. So this is some really famous work from Jared Kaplan. I think, was it OpenAI? Is he at Anthropic now? I can't follow. So this is with compute. We also have data set size and the number of parameters, and this just shows you get power laws everywhere. So things actually look like they work pretty well, at least in one dimension at a time. So you could ask, like, what do these look like in astronomy and different tasks? It's going to be dependent on the field, but we did run this test. So Mike Walmsley, who's a Dunlap fellow, who's going to be starting at Wave very soon, which is a self-driving AI startup. He did this project with the Zooniverse, which is a crowdsourced citizen science data set to label lots of properties of galaxies. So here's a couple wonderful pictures taken from all these different surveys, showing like the types of images that were shown to many hundreds of thousands of volunteers who kindly took the effort to actually label these with tons of different things. And so he, went to work trying to build different machine learning models to try and ask, what does it look like if I run the same experiments on this data set? Here's what he gets. So main thing is that there are a couple of different model classes. I don't really want to go into all the different ones, other than a couple of these involve some transformer stuff. And then some of them are like normal convolutional things. The main thing is that you just see the same scaling relationships across all of them. So in this case, it's the more images you have. This is the number of parameters of the model, sort of going from smallest to biggest. And you get to see, yep, it sort of decreases this way, it decreases that way. We've done tests, they all look like power laws. So we do see the same general behavior. If you summarize this, in general, what we find is that the trained data set size has a greater effect than model size or architecture, but you can still make a lot of gains by adjusting your architecture to be more efficient. At least in astronomy, this seems to be the case, but I suspect that very soon that we are not necessarily going to be in the data limited regime, and we're really going to want to think about how we can scale models better for the era when we have lots and lots of images coming in all the time. So with all of this, I'd say like we do have a choice now. It's a little bit different than in the simple case where we just have an optimal thing. We're now sort of balancing this trade-off between amount of data we're using, amount of compute we're willing to take, and the complexity of the model. And together, these will give us some model that we're going to be okay with. This also asks general questions about how we select models, but I don't want to go into that here. But I'm very, very happy to talk about model selection as like a statistical problem. So finally, you might get to this last part on complexity. And so for me, I sort of was like, at this point, I'm like, okay, I don't know if I can keep up with the literature at this point. It's moving very, very fast. But hopefully, at least you guys are either feeling the same as me, which is very reassuring. Or if I'm not doing a good job, then hopefully this is a way of saying at least I'm aware of that. So just as a recap, like we talked a lot about like these different things in the model and how it's really important to think about these neural networks and deep learning as about learning features and learning structure. And the fact that when it comes to parameters, those don't really matter. What matters is sort of this underlying feature, underlying circuits that these models learn, and the correlation structure that you assume when you create a model in the first place. For traditional models, these are the same, and they're not true for these big AI machine learning models. But once you understand this and you know what you're looking for, then it's okay. You can sort of take these, convert them into these other representations and say, great, I can still get insight out of this. I still can understand what they're doing. I know the building blocks, and I know the principles, the conceptual principles upon which they operate. Learning, of course, is hard. We've talked about interpretability, but interpretability is not the same as discovery, right? It's not the same as understanding. One thing that is clear is that we have a lot of agency in how we apply these to science because we get to tell the models how we want them to learn, both when we design the models and also when we feed it data and we establish a loss function. Everything is about trying to help the model find the right things that it wants to learn. We don't tell it those things explicitly anymore. We get to give it general directives and it will be able to pick that up directly from the data. And that's more powerful. That's sort of the big lesson from Rich Sutton's bitter lesson here. Now, when it comes to these things, I like to think of these two regimes of the universe. One is sort of a very physicsy thing. That's physics, that features can be very dense. We have all this really complicated stuff around us and we say, oh yeah, this can be summarized by 4 forces and like these 10 coefficients in the standard model, and that explains everything in the end. So we see a lot of stuff, but there's only a very small number of true parameters that matter, that generate lots of this complexity. You also have the sparse case, which is that you have many more things that actually exist. So when it comes to language, sure, there are many words, but the concepts that exist can be beyond words. You can have things that you can't vocalize, but you know are there, right? Or words can appear very rarely, but they can have a huge impact on like what you're trying to say. In this case, for language, you could think of things that are very sparse. So you have very high signal to noise, but very rare, or maybe very low signal to noise, but very common. Saturation often occurs when the model has learned all these relevant features. And when this happens, and depends on these regimes, depends on these scaling laws, it's not just dependent on the parameters. Now, where are these features? A lot of strategies rely on autoencoders or similar things. This is the idea that you take a very complicated model and you say, well, if I force you to learn some simple representation, and by force, I mean you kind of have to learn 5 numbers that reproduce the data with some restrictions, then that's maybe more interpretable. And whether this is a dense autoencoder or a sparse autoencoder generally depends on what regime you're in. Sparse autoencoders are very popular now for trying to understand very big vision language models, for example. In this case, all I can say is, Anthropic does a lot of good work here. There are great papers. This one in particular on the left, this toy model superposition, amazing paper. And by paper, I mean blog posts. So you can find it on their website. I think it's great. They have new ones. The literature is great from lots of companies. So I would say definitely check it out if you're interested. On the dense side, which I think is maybe a bit more accurate in some cases in physics, but maybe not everywhere. We tried to do something like this to understand stellar spectra from the Gaia survey. So in this case, what we want to do is integrate lots of these lessons together. We have noise. We are trying to infer these types of very complicated stellar parameters, and we wanted to sort of condense them down to a small number of things. And so that was sort of the idea. Here's sort of what the data looks like. If I zoom in here, what you can see in this little snapshot, these are 2 different parts of the Gaia satellite spectrum. This is essentially intensity as a function of wavelength from 2 different arms, BP and RP. And as the star changes in temperature, you can see how the particular shape of the spectrum changes. So there is some underlying parameter for how stars evolve that govern a lot of how they look in practice. And we want to uncover some of the structure without ever telling the model what this is. So our idea was we just added some extra terms to account for noise. and the fact that we never actually see the real underlying spectrum. We always see noisy realizations of the data. But can we learn like the true thing just from leveraging the fact, making two assumptions? One, that we sort of know what the measurement noise is, and two, that probably across all of the data, some are more similar to each other than others. And so maybe we can kind of do some pooling for nearby things and have the model learn how to average adaptively different noisy stellar spectra. So that was the idea. We just have it predict the same things at the result. It knows nothing about stars. It's just with data, and there's no ground truth. So how does it do? We thought it did pretty well. So here are cases where we give it ground truth. These are temperature on the x-axis. The y-axis is log g, or surface gravity. This tells us how big the star is, essentially. It's a combination of mass and size. And you can see in this latent representation on the right, where we've taken some two-dimensional projection, as we sort of wander across in the physical parameters that we care about on the left, we actually do get a nice decomposition on the right, which corresponds, roughly speaking, to where we expect things will be. This also shows up in other ways. This is with metallicity, or the chemical composition of stars, which is shown here on the left. So that's essentially the true results are in the middle. We're showing you these tracks that sort of go across the true data. And on the left and right, you see projections of this in this autoencoder. And so yes, it learns that this type of chemical composition is a really efficient way to represent real data. So again, we don't told it anything about this type of stuff, but it shows that it's learned to organize itself in a way that seems to at least align with things that we've seen before. This isn't kind of discovery in some sense. We're using like real data to interpret the model, but it's at least a good step showing that ways that these models learn to organize data do adhere to some of these principles. We can also do the same with different types of chemical compositions. So this is showing alpha abundances. These are things like magnesium and carbon and oxygen. And the fact that we can actually distinguish these with this data as well, even though the data's quality is not necessarily very good. Anyway, so the main thing is that this actually works. This approach uses real data with noise and accomplishes it. I don't even think it's that clever. It's just more that you can actually combine these ingredients together and make a model work that does all the science things that you want. And anyone can do this. I encourage everyone to think about it. So that's kind of the end. So again, I just want to put an asterisk on this, because if we had solved this problem, then I think we would be less worried about the machine gods. But for now, I think it shows that there's real potential in some of these methods to make a lot of headway. So I want to close by just kind of coming full circle at the end. And for this, I just want to say, I think, stepping back, right? When we think about what we want to do as scientists and how we want to interact with data, our relationship with data and with these models has changed a lot. We started, way back in the day with storytelling. We want to understand the universe around us, and we did that by telling us stories that encoded lots of information about all sorts of things, historical events, weather patterns, particular sky locations of things. They're very information dense. So a lot of indigenous knowledge is actually really well encoded here. And over time, that became systematized in writing. And then that writing became kind of systematized in terms of data collection. So now we started collecting data the same way, storing it different ways to make it more amenable to things like math, right? And statistics. So now we can start having this language to say how we can use some of these measurements together. Then, of course, we get computing, right? We're trying to take this data, and now to even access that data, we need to develop an interface, a separate language to be able to communicate with that. So we're getting further and further away. And now in some crazy way, we've come back, right? We've come full circle, where our way that we engage with data can be, it doesn't have to be, it can be very humanist. We started by telling stories and engaging with the data directly with people. And we can potentially come back to that, where these models give us the potential to also be able to talk to our data, to talk to other people and have it interact with us, rather than always having all these barriers in the way. And potentially being able to use lots of this to make that happen would be a nice story if we don't all die in nuclear war. So essentially, I just want to end by saying, I hope that gives us a good motivating question, and hopefully you feel I've answered some of the how, not necessarily the what. And if you have questions about the different topics we covered, from double descent to sort of this feature learning paradigm, I skipped this example, to kind of like feature representation and learning, some of the applications of these for stellar rotation, scaling, galaxy, images, encoding, information content. We try to cover a lot of ground I'm super happy to hear anything. So thanks, everyone. Hopefully it wasn't too late, and happy to take questions.
Much, Josh, that was great.
Interested to hear more about your statement of architecture as sort of a prior.
Yes,
Does that extend in your mind to like weight initialization and then
absolutely.
ablation studies?
Yep.
Because I'm kind of interested in thinking of that idea and extending it to the way we think about equations applying, if you're thinking about planetary dynamics,
Yeah, yeah.
thinking about a certain set of equations, hydro, it's a different set of equations. Seems like what's happened in astronomy and broadly
Sorry.
in the physical sciences meets AI is we tend
Yes.
to kind of grab model architectures and learning approaches from the literature that are
Yes.
more data appropriate than
Yes.
they are topic appropriate. So are you thinking about this in sort of like composable units, like we think about bringing a set of equations to certain sets of problems?
Absolutely. So I think, so there are some, essentially the weight initialization is really key. So in like the neural network Gaussian processes view, where you're kind of averaging over all possible random initializations of neural networks, that one is directly dependent on the specific weight initialization structure that you pick. So in that case, picking a different one will generate a different Gaussian process with a slightly different kernel. And so that's direct. But also it very much is the case that different units you pick, different activation functions you pick, different ways in which you allow for weight sharing, all of those actually are composable parts of this kernel that will give you different structure. And so you really should think of it like an equation that says, I kind of want to have some sharpness and some smoothness, and I want some locality, and I want some temporal dependence, and building your model in that very modular way. And you can explore some of this yourself. There's a nice package that I think is archived now called Neural Tangents, which allows you to create and easily, test some of these infinite width or finite width approximations of networks. And so I would say that I do see a lot of this the same way. Yeah.
But are we in this kind of weird space now where the only people that are gonna push the envelope are the ones that know enough about the literature to know, like, oh, you use cinch in this layer and you use atom for this, and it almost feels like you have to be this kind of creative artist who knows literature to do equivalent of what we used to do with physics and say that's
Yes.
gravitation, right?
I think there is a risk of that. I'm hoping that through the advent of like software and good practice, that people can feel more comfortable like getting this intuition by running experiments the same way that we would for things like ArcSync and using certain mags or certain transformations. We get those through a lot of like domain, expertise, or just over time, we see a lot of data, we kind of figure this out for ourselves. I think the more we can encourage students and practitioners to experiment in this way, so they can kind of get this intuition as well, I think that helps. But for now, I agree that I think the barrier, there are some things that are easier, and then there are some parts I think that are pretty difficult to sort of just say, oh yeah, you definitely want to use like these particular types of components and these residual connections. Because yeah, you just have to have some encyclopedic knowledge of all these tricks that people do.
So you offered a story on interpreting, at least in a training phase. Do you offer maybe a story about how like post-training or in context learning might be interpreted?
Yeah, so I do not have a good story there yet. Well, some of this is that I think post-training, you can do some stuff. In context learning, I think is tricky because it's a lot of interesting conditioning happening there. There's similar things like with chain of thought potentially being in context learning, where what is it doing? Just generating a bunch of tokens. It hasn't seen anything new. It just generates more things. So no, I don't have a good answer for that yet. My hope is that there will be something that's just as clean, and we can. I like kernel regression. I like kernels. I like kernel learning. I like the traditional stats things. So my hope is that we can sort of have some purchase to figure out how this is happening in that context, but I don't have a good answer for you right away.
Thanks. Are there any questions? Oh, sorry.
Great talk, thank you. I got a kind of question on I guess it would be the double descent kind of capacity
Yes.
capacity for data saturation
Yes.
kind of question, and thinking like in a very classical and simple context, say we have a problem that we can cleanly frame with Fourier approximations,
Yes.
classical spectral theory.
Yes.
We land cleanly on an Nyquist limit, and we kind of understand that trade-off very cleanly, right? Between bandwidth, capacity, the structure of the boundary conditions of the operator involved, and what the data can do.
Yes.
I'd love to like hear your thoughts on like that toy, nice, clean, digestible example when mapped to these problems with so few assumptions on data operators and the structure of the models, if you will.
So I would love to be able to come back and say that there's an equally clean thing with a lot of these methods. For some of, I think, like these really shallow, like 1-2 layer models, like you can come up with similar things where you can get very strict bounds and lots of these conditions. But in the big ones that often, very nonlinear, you don't. I think you can come up with some approximations where you can say, well, kind of, if assuming the kernel's fixed or that changes very slowly, you could probably derive lots of similar constraints with spectral theory. I really like this view, but I don't see a lot of things in literature on this. And I think it does become more complicated with feature learning and the fact that the kernels change a lot, from iteration to iteration. So I would love to have a simple explanation. I believe that one is possible. I just have not found it yet.
But even absent something as like theoretically clean as kind of traditional Fourier analysis, right? Can you imagine building at least practical tools, because you were pointing at software, right?
Yeah.
Ways in which we can instrument tools to give practitioners at least, even if they're heuristics, but
Yes.
concrete heuristics on these trade-offs.
I think
That
so.
even if we can't prove these things down to first principles, right?
So I really think that we can. I mean, the idea that you can find some eigenspectral alignment between sort of what the model looks like at a given time, maybe potentially factorized, because of course the full matrix is very large. But you can use, I can imagine either random sketching or factorized or simple like low rank approximations. You can show how that changes. You can look at how that projects onto the data, in like a kernel representation sense. I think that would be great for potentially monitoring how well the model is doing and sort of the generalizability of the structure it has. It also, I think, would be great for understanding spectral bias, very generically in neural network architectures, and some of the effects of allowing for residual connections and skip connections that allow you to essentially have data transfer and connections between layers, and instead of always having things be hierarchical. So I would love to have those tools. I'm thinking a lot about whether you can build them. I have not seen a lot of this in industry, but I'm not convinced that that's because it won't work. I think it's because a lot of people in industry are not really in like this sort of spectral theory, kernel learning like mindset when they're looking at this problem. Yeah, so I don't have a good answer for you, but I would love to make those tools exist.
Josh, are there any questions on the Zoom?
I do not see any. There are only 3 participants right now.
Okay, great. Well, before I break the rest of the room, let's just thank Josh one more time. The rest of the day, meeting with some folks.